Hello. In this video, we are going to see about QNX NTO architecture. So, so in this, we will be covering up the core architecture of its Neutrino real-time operating system and how it differs from the conventional monolithic system. This QNX Neutrino trust belongs to microkernel design. And its key components such as PROCNTO, IPC, and resource managers, and process thread and scheduling. So let's dive into the core architecture part. So before getting to know about the core architecture, so I would like to give basic differences between the kernel types, that is monolithic kernel and the microkernel. So if we see the monolithic kernel, there the file systems, drivers, network elements which are present on the stack, so which is going to be running in the privileged kernel space. So suppose if there is any issue happening in one end, for example in a driver end or a file system, that can crash the entire operating system. So this design is considered to be a large complex one and it is less secure. But whereas if you see the QNX microkernel, so only the scheduling and the IPCs are in the kernel. So other than that, the drivers, file systems, applications, so which is going to run on their own allotted space. So that is the key differences between the monolithic kernel and the microkernel. So that is why uh, the QNX, so is going to be having its own reliability. So based upon the visualization shown here, so if you see the monolithic one, here, as I said earlier, the network systems, file systems, the memory process drivers, all these are going to operate in a privileged mode. They are going to have a common memory space. So that is why if any particular unit or block, if it's supposed to not perform on time, it induces some kind of critical errors. So that the other file systems will be depending upon the other systems. So that in turn will crash the entire operating system. So in the case of microkernel, that is QNX, it is not the case here because we only have the IPC's schedulings which is there on the kernel, and the rest other files such as network elements, file systems, drivers will be operating on their own memory spaces. So this is how this NTO is going to have its own reliability. That is why it is claimed to be having a high fault tolerance. So this PROCNTO, that is considered as the heart of your QNX. So this PROCNTO stands for process, and NTO stands for neutrino. So this is PROCNTO. Here this is having the two key components. One is the microkernel, other one is the process manager. The microkernel will be able to handle only minimum part, that is the threads, schedulings, IPCs, and interhandling. But whereas if we see the second component, process manager, this is going to manage the resources. So whether based upon the task it is running or the process it is having, or inside process we have multiple threads. So we will look into the differentiation between uh, process and threads. So here if you see one side is we are having two process A and B. Other side we have the server name, that is the process which are happening at the servers. So this is commonly referred to as file descriptors. Using this, the processes are able to complete their own set of activities. So in the case of IPCs, that is inter-process communication. So we can enable this kind of communication either in the form of messages or pulse or signals. So now what is mean by a message? So message, it is a primary way to exchange the data. Using this, you can able to send a message to anybody. For example, if we have a client server model, the client will be sending a message in the blocks and the server will be able to receive that and process it and it replies back. That is how the message communications has been taking place. And the next form of IPC is sent in the form of a pulse. So pulse is considered as a short communication notification. It is said to be asynchronous one, and that is why it is considered as it is highly useful for lightweight events and notifications. The third type, it is called as a signal. So we used a signal so in order to represent for events like if anything wants to get abruptly and terminated, or if any kind of an error occurs, if you want to terminate that by passing an interrupt. So this particular kind of a signal in the form of an IPC can be sent to make that happen. So now we'll see about the comparison of the major differences between the process and the thread. So process to be having its own example. So I'm considering that the process is going to be like a container. So inside container, you will be having multiple resources like memory, open files, and timers. So it provides its own address space, so isolating it from the other processes. Whereas thread, it is actually just a unit of execution. It is just a program code. So it has its own priority, and if that entity is getting scheduled by the microkernel, it will perform that particular task. So a process may contain multiple threads. That is the major difference. So there are various scheduling policies for QNX. So one is FIFO, first in first out. In the first in first out, the thread will be running so until it's get blocked. So that is it will wait for a message if it's getting preempted by a higher priority task. So then the priorities will be given to the other scheduling. This is how it happens. In the second case, it is round robin. It is similar to FIFO, but the difference is it is based upon the time pattern. One after the other, and after that, another process is getting run. So thread only runs only for a fixed point of time. So before it is getting moved to the priority queue. The last scheduling policy is called as sporadic. So generally, the sporadic scheduling here, a CPU will be given time. That is, it guarantees that we can use this particular process to perform a particular process. Inside process, we told that it is having multiple threads. To perform that particular thread activity, the CPU will be given time to perform. So that time will be coming on or after every time second frame that we have to fix. So here example given is 1 millisecond of your CPU time every 10 milliseconds. So this is how the sporadic scheduling policy happens. So it prevents the CPU starvation. So it will not wait for its turn. And the resource managers is going to be a key concept for this. So using this, they are able to process so own part of the path namespace. So this is how the drivers look like a part of the file system. This is considered as a secret sauce for this QNX operating system. So let's see about its advantage. So first advantage is going to be the reliability. So we said earlier it is going to be a lightweight, and it is small, and QNX architecture, it is following a microkernel type. So if anything fails, for example, if a driver failed to perform a particular task, so it can be restarted in milliseconds without rebooting your system or affecting your kernel. So that is how it proves its reliability. And next one is scalability. So we no need to have some kind of networking element. So it is not going to run its own IO sort process. And development, the drivers can be developed and it can be debugged just like any other user applications. So let's see about the boot sequence it is going to have. So for a QNX NTO architecture, initially the program is getting loaded on the, that is, it is called as IPL, initial program loader. Here hardware specified code is there that is going to initialize the CPU and the RAM part. So next stage it is startup stage. So what it does is in the stage it will set up the system page, and it will find out for the PROCNTO image. And in the PROCNTO, the kernel and the process manager will be starting as PAD1. PAD stands for process ID. We are naming it by giving a number, process ID 1, PAD. So that is going to act as a root of the total system. And the fourth stage is the boot script. So upon initializing all the things, so such as drivers and applications, so based upon the boot script, so this proc NTO will be launching all those things. So this is all about the NTO architecture. Thank you.